So today, very excited to be joined by Professor James Nowick out of the UC Irvine. I actually want to start with this because your open access videos in UC Irvine, extremely helpful for undergraduate chemistry, graduate students, anyone that just wants a refresher in chemistry. You know, you were one of the pioneers who basically had open access to UC Irvine. And so that is certainly very helpful to anyone out there. I particularly liked your course in organic spectroscopy. So nuclear magnetic resonance, IR, and mass spec I found it actually extremely useful for my graduate studies. So I'm going to give a quick shout out to, if people are interested in spectroscopy and organic chemistry, to go check out your website on YouTube, which I will link in the description for anyone to check out. I guess I could start with this is, because I noticed that your videos kind of came out in that 2020 year. So a lot of it was during that COVID. So had you had thoughts about doing some sort of open access form of instruction before COVID, or did that it just kind of worked that way?
Well, I actually did the first of these in, I believe it was 2009, and it was my sophomore organic chemistry class. And what happened, and this is really the inception of this whole thing, what happened was the university was having a tough time with budget, and they said, well, we're going to have to cut a bunch of stuff by 5%. And my view was, I don't want to do extra work to take a course that works nicely in, I think it was 28 or 29 classes, and cut it down by 5% and try to make it all work together. You know, if they're cutting classes due to budget issues, well, we'll just have a couple of them video recorded so the students can still get the same amount of instructional content. Anyway, I set up the machinery for that, and the folks from the office on campus that does various video recordings said, hey, would you like us to record the whole class and not just do a studio recording of a couple of lectures? And I said, sure, that sounds good. As it turned out, the university was not so short-sighted as to say, oh, we need to cut classes by 5%. It was, we'll cut, other time. We'll basically use this to say, okay, accomplish the same amount in less time and it wouldn't affect classes. But by then, the mechanics of having the video team come in was already set up. And I was putting the videos up on the course website and said to the team, hey, we should get this up on YouTube. So they posted all of this on YouTube, and it began to take off. And it was sort of fun because you'd see people, comment from around the country and around the world and enjoying and benefiting from things. And it's like, this is cool. It doesn't, you talk in a room with a class, the words evaporate. Here you catch them, and some people seem to benefit. And so I did it with several other courses. I think the next one was the organic spectroscopy class in 2011, which was a graduate class that I'd been teaching. And then there was my another organic class. One was our first quarter. We're on the quarter system, so 51A we call it. And then I did another as 51C. I think that was 2014. And then I thought, oh, this is great. I'm teaching this advanced organic class, undergrad class, so basically junior, senior level class. I'll do it for that. And I did it. And then when the pandemic hit, and I was giving my spec class out of my living room in 2020, and we were, all used to Zoom for better or worse, it's like, well, I can video record the whole class and do that. And so that one went up there. And that one I would, so the 2020 version, I felt was more refined and polished than the 2011 version and had some new content in it. So that's the one I think you picked up on. And then recently there was another 51A class that I did that it was okay, but I used the Zoom I use the Zoom technology there in the classroom to record and broadcast it from the class. So all of this got picked up by the dean and the dean of the continuing education as, oh, we should go ahead and sort of package this under an umbrella. And then I recruited some of my colleagues, and so we've called it Open Chem, and we have most of our undergraduate lecture classes on there. It's not meant to be, a MOOC. It's not meant to have testing content or certificates of completion. Many of us, myself included, make available content on websites so people have access to handouts and exams and so forth. But it's just purely for people's benefit, because with a little bit of more, work, once you set up to video record the thing, you can make it available on YouTube for other people.
Yeah, I think I'm going to pick your brain about this a little bit, because with the whole movement of, let's say, like chem archives and chemical science, like open access journals that aren't necessarily peer reviewed, but you can kind of get your stuff out there quickly. And there is, with like Chat GPT, like we're kind of moving to this open access world. What do you think the blend should be between, let's say, university setting and that, because this is something that I spoke about with my PI and other professors as well, is that in some sense, it's like, okay, if you wanted to learn chemistry, like how do you actually compete with anything that's online? Like, is there certain benefits to like a university setting and college setting versus like open access? Obviously, like, I guess the open access is not accredited, but the content is pretty good, right? So, and then is there a desired blend between both of them, really? I don't know what your thoughts are about that.
Yeah, absolutely. At the end of the day, it's easy and fun to watch videos. Mm-hmm. Organic chemistry in general involves a huge active learning component of actually working problems. And even if one's in a traditional lecture class, which is what I tend to teach, there's a substantial content of homework and working problems. The graduate spectroscopy course I teach is well known among our students. The problem sets sometimes exceed 100 pages in length. People work for hours and hours and hours. We reconvene and discuss the problems together. The final exam this year was a 3-day affair, where, it was at home, take home, but it was, a huge thing. And that's where the learning comes. I mean, honestly, in terms of, and this is different for undergraduates, but in terms of graduate students, at the end of the day, nobody's going to care what letter grade you got in a class. In our program, whether it's an A, an A minus, a B plus, or a B, if you're in that range, basically, sure, it's great to get an A in the class, but the real benefit at the graduate level is up here. These are the foundational skills for solving your research problems. And so, I'm not making these problem sets. I'm not making these exams to evaluate people. I'm making it because that's where the learning occurs. And at the end, the grade for at least the graduate class is only the smallest of pat on the back that I can give people to say, good job. And they can feel good about for themselves, and their PI probably isn't going to know, and their employer probably isn't going to know, and nobody's going to care. But in the end, it's really hard being a PhD scientist because you got to be excellent.
Yeah.
And you got to be excellent to tackle tough research problems. You've got to be excellent to be out there in a leadership position, in the future, whether it's academia or industry or policy or anything else. It's that level of excellence. And so that's what one is really getting out of that. Very few people have that discipline to do it on their own. Now, ditto in terms of the undergraduate level, but I'd say less so in the sense that at least at the sophomore level, you have a range of people with different goals taking the class. Most of them, many of them want to go on to med school or pharmacy school. Some want to go on to be chemists.
Yeah.
And in that case, you might say, okay, getting the grade or whatever may be the primary motivation. And yet I would say that self-study isn't going to get one there unless one is truly exceptional and has that type of discipline to actually work the problems, in which case they may well do fine on their own with a textbook. So then we come back to, okay, what's the point of all of this? And the point becomes that people can get access to what I'd like to think is good quality instruction or supplemental instruction that can help them learn. I know I use resources like this all the time. When I want a primer on something scientific that I'm not familiar with, that's not in my own area, Wikipedia may well provide a very good generic primer because someone who's presumably reasonably expert has written something about it, and it's been sort of peer edited and peer reviewed. Now that's, by the Wikipedians, if you will, with people doing everything from flagging weasel words where you have an uncited assertion to, looking for primary references. And most of them are pretty good there. Now, one of the big things moving ahead people are going to need to be able to do is learn how to critically evaluate different information sources. This comes with anything from health information. If I want to look at, best way to treat, an ulcer or something, or high blood pressure, whoever's got the money in the game is going to be paying for high-end things to show up high in the search. So if some nutraceuticals company says, our, vitamin, whatever, herbal extract supports immune function, that's a great one, because those are the types of weasel claims that skirt right up to the line of FDA. So I'm worried about getting a cold, say, and I look, what can I do to prevent getting a cold? And, right up there becomes, I don't know what, Herbalife or I don't even know who produces this type of stuff, but somebody who's marketing something that, supports immune function. I need to be able to look critically at that. Now, you mentioned ChatGPT, and this is fascinating because we are right on the edge of things, much as when Google came out. And I remember a colleague telling me in the late 1990s, mid or late 1990s, this internet thing is coming out and everything's going to change. And, little did I know just how much it would change. So you go ahead and right now, and I've looked, because it'll be really interesting. There are real potential uses of these types of massive, what do they call them, massive language, constructs, the ChatGPT. Sure, yeah. So a great experiment to do is, say, ask ChatGPT to give a bibliography on a subject and provide the most important citations. And right now it's incredibly lopsided. It can be valuable, but it's probably like asking a sophomore undergraduate to provide you with that information. You're going to get some hits, some misses. So I asked it, one of the areas we're researching in my lab is an antibiotic teixobactin. So about 2 months ago, I asked it, I said, provide, some leading references on teixobactin. I was curious. And I was blown away that it made reference to a paper that I just published. So then I asked it the same question, and I said, and provide citations. And it cited a completely different paper. So, as these tools appear, whether it's Wikipedia, whether it's Googling things, whether it's Science Citation Index or Reaxis or, Google Scholar, one needs to get skills in critical thinking. My colleague who's teaching a chemical biology course basically incorporated this in her, winter quarter class and asked the students to have ChatGPT do something and then ask them to provide a critique of it. And that's exactly the sort of skills that I think young people need as they sort of move along and navigate new sources of information. But at the lowest level, one can always get things that one takes, uncritically and end up with, a mix of something that's valuable and something that's garbage. I asked it for some leading references on the synthesis of, I think it was morphine or strychnine. Mm-hmm. And it was interesting. It was all classics from like the 1950s, 60s, Woodward, other papers, but very sparse, if any, on modern references. So it completely sort of viewed by popular view. Probably the same if I asked, I don't know who I would ask, but if I said, who's the best musician today? Who's the best rock musician today? The type of answer, it's an unanswerable question, right. But I suspect if I asked, Google or, somebody, you ask a dozen people, you'll get a dozen opinions. And so being able to say, wait a second, that doesn't mean that I should buy this album. It's kind of the same thing. It doesn't mean I'll like this album.
Yeah, I think I saw a Twitter feed where they were talking about the, I don't know if morality is the right word, but like having it write like an introduction or an abstract for like scientific papers. And I guess from the newer generations, the thought might be, well, if it's accurate, then like who really cares? But I don't know. It'll be interesting to see how the implementation of these like AI move into science, especially in like I would say the physical sciences like chemistry and physics, where that kind of goes in the next few years. So I'm very curious.
It will indeed be really interesting. One of the things I give to my own graduate students as piece of advice, we work very closely on writing papers, and there's, literally dozens of meetings back and forth. Mm-hmm. But there are two things I always tell people. I say, one, nobody has to read the stuff that you write, except I don't say stuff. And two is, why are you telling me this? And this really applies to an introduction. Yes, one can put and I'm guessing, coming back to my teixobactin example, I'm guessing that the language models and so forth and specialized ones written for the sciences are going to become better at this. But at the same time, I come back to, why are you telling me this? What are the things that are relevant to the paper that you're writing? Because in the end, it's going to be machines writing the papers, machines reading the papers. Is there any point in publishing a paper? What becomes the point? And it's, I believe right now it is the human intelligence that's going to be making those really critical decisions on what are you telling people and why are you telling them this? Why is it relevant? I'm not a huge fan of overly lengthy introductions. I think that one should do the appropriate level of scholarship, but again, be critically saying, okay, why are we telling the reader this? If it's something they already know. We work also in the Alzheimer's area. If any introduction basically spouts, sort of facts and figures, and it boils down to Alzheimer's disease is bad. Okay, the reader knows this. I'm sorry. any reader knows Alzheimer's disease is bad. What are you bringing the reader to engage them? That reader is going to, whether it is the broad audience, whether it is the highly technical reader, Alzheimer's is bad. You basically need something, and it's probably not going to be the number of billions of dollars in cost and lost productivity. Maybe it is, but then the question becomes, okay, what's the purpose of this? If it's that they really ought to pay attention, sure. But again, nobody has to read the stuff that you write. Does anybody really care about those facts and figures if they're not a policy wonk? Is it really coming down to something else? So each sentence, and certainly your first sentence, certainly the lead-in and an introduction, you need something that's going to actually engage and inform readers at a variety of different levels. So, put some meat in there. And I don't yet think these types of, software models are in that particular, able to do that yet.
Not yet.
But I think not yet. And it does beg a lot of questions.
Yeah, I think it'll be very interesting to see what happens over it, especially because when you think about, oh man, you definitely know that paper that was basically forged. It was a natural product synthesis that was basically faked.
James J. Leclerc's paper.
Yeah.
Yes.
And you think about that kind of paper where it's like, okay, that was just written by some guy. It's like, what can an intelligent AI form up, basically? And how does that get past review? I'm very curious to see how that happens, Yeah,
if you're talking fabrication from whole cloth, that's a really interesting point. And again, that sort of comes down to why is one doing or publishing science? And for that particular paper, I cannot understand the mindset. And after that paper came out, my dear colleague Scott Rognovsky, first pointed this out, and then I looked at the paper, and I was teaching my NMR course, my spec course at the time, and I noticed there were no C13 satellites on methyl peaks there. And if you've got a methyl singlet, you're going to be able to darn well see a C13 satellite. It's only 0.5% the height of the singlet itself, spread evenly around the sides, but you can invariably pick them out. I sent him an email. I got some massive bunch of gobbledygook. Actually, I think he actually called me. We had a very interesting conversation where he talked about inviting me down to the Zenobi Institute, which I declined on. But anyway, it was an unusual conversation. But I truly do not understand that mindset. And ditto. Okay, I think, and this comes to the issue of graduate mentorship. If a research advisor pushes a student for the desired result, they're inviting getting the desired result, whether that result was gotten or not. And, where does the fault lie? That's a really interesting question. Now, in the Alzheimer's area, where it was clearly, there's another example with an amyloid oligomer, which is an area that we're in, called A beta star 56, where gels were fabricated or manipulated. I mean, this was something where I think it's pretty clear it was the lead author of the paper. Again, that sort of puts it in the case of the fabricated synthesis paper we were just discussing, where it just doesn't compute for me. But on the other hand, there's a very high profile story in the, the case in the Breslow group was different.
What is that about? I'm unfamiliar with this.
So this was out of Columbia University back in the 90s, maybe 80s. where a paper got published in JACS where there was Professor Breslow, now deceased, has been working for a long time at asking how do you do CH activation in steroids? Well before the word CH activation was there. This was sort of a touchstone from the old days of cortisone synthesis and other steroid synthesis and the advent of the birth control pill. And Breslow basically said, enzymes can go ahead and functionalize a particular CH group in a steroid. Why can't we? And he sort of set out with this as a guidepost for a program of chemistry that ran many, many years in his group, decades in his group. And one student produced a result. And I think this was a case of, I don't know, because I don't think it was undue pressure from the advisor. I think this was a case of a lie snowballing, and it became very sophisticated with swapped NMR tubes and someone else verifying the results, but the students swapping NMR tubes so that they get the desired result. It was you could only believe it in fiction. And the spouse of somebody who was in Columbia at the time actually wrote a novel about this whole story called Catalyst, which is worth reading if one can find it. I think it's out of print currently. Anyway, but you ask about this mindset, because there are different questions. There's the question of, can machine learning approaches be used to various aspects of writing papers? And it's beyond my sort of ethical, I'm not an ethicist. I think the answer is going to come down to yes in various ways. I suspect, for example, it's already extremely useful to be able to have it. No, it is moderately useful to be able to say, here's a paragraph, copy, edit, and proofread, and indicate the reasons for the changes you've made. And that's a reasonably low-level, concrete task, not that different from the spelling checkers and grammar checkers that we, increasingly have built into Word and other programs, where sometimes Word will catch a subject where you have a complex subject and a verb far away. Sometimes it will catch a subject-verb disagreement. Sometimes it'll be off the mark. I still need to look critically, but occasionally I'll say, oops, I goofed. Yep, I need to change. It's indeed a singular subject, not a plural subject. I need to change my verb. That's useful. I suspect these types of features are going to get incorporated more and more widely and just be part of the routine thing. Then you come to these more big picture questions like write something intelligent about some data. Maybe, although again, I look at what the draft that a beginning student gives me and how hard it is to form a paper, how we worked so hard together to form it. And it's a long, long road, I think, from getting to that point. Some of the low-level scholarship provide a bibliography of leading references, probably. I mean, right now, what I do is go into basically what used to be, it's now Web of Science. It used to be Science Citation Index. And you go ahead and you'll look sort of for leading papers based on citation, based on primacy, based on journals, and you'll say, okay, I'm compiling a bibliography. You read the papers, you read the abstracts, you say, here's some leading work. These have been the contributions of this. This have been the contributions of this, and that helps in your scholarship. So I can see some of that being useful in a limited context, but it's going to be strange moving ahead. I know that Nature already has gone ahead and drawn opinions about authorship, that these programs, cannot be listed as authors, but much in the way that one may acknowledge somebody for helpful proofreading or copy editing or suggestions, it may be possible and appropriate to acknowledge, that this was done by this,
Yeah.
or much like maybe a student in my lab, without making contributions to the main research of a project, will have contributed a chemical compound that they synthesized to it, but it's a compound that's maybe a literature compound or something we've already published, and maybe it doesn't rise to the level of authorship.
Yeah. Strange times for science, but we'll see where it goes over the next few years. We'll keep a close eye on that. You kind of touched on it a little bit, so I'm kind of excited to dive into this in your research. So generally speaking, you work in small molecule synthesis and peptide synthesis and like protein expression. Now, some of the peptides that you work on, and I think you mentioned it, so teixobactin,
Teixobactin is one of them. It's an antibiotic that caught my attention when it came out. Mm-hmm. Actually, it caught my attention first in the New York Times. It made the front page of the New York Times, which made me run to get the Nature paper and then go to my group and say, hey, does anyone want to work on that? So we've been in since the beginning, since the initial publication on that one.
I was going to ask because I feel like there's thousands. I mean, I guess you could say this about all chemistry, really, but there's thousands of like peptides and maybe possible drug development. There's so many ways you can go into. How do you like decide on, okay, we're going to work on this peptide and the analogs of that? So like how did those kind of things come about?
So it's interesting. So many people in my sort of peer group in the peptide community have been working in the area of what's called antimicrobial peptides. Antimicrobial peptides are often defense peptides, either made by one's own immune system as a first line of defense against pathogens, or made by various other organisms. And for a long time, the vision has been, hey, if your body, or if a frog or whatever makes a particular peptide that kills pathogens, maybe we can harness this peptide as an antibiotic, as an antimicrobial peptide. And I've watched that area for a long time, and the advances have been tough in coming, in part because many of these are sort of generically cytotoxic or hemolytic. So basically, if you're going to be using these in the bloodstream against an infection, you risk cleavage of blood cells because they are generally active toward membranes. And there are just small differences, not tiny, but, there are differences, but not gigantic differences between the bacterial membranes and mammalian membranes that mean that you get a relatively narrow, what's called therapeutic index. In other words, the index where it will be toxic to bacteria, but not toxic to the cells of the person who's being treated. And so I never felt my lab had anything serious that we could contribute in this. When teixobactin came out and I saw, A, it's a peptide, B, it's new, it has a cool mode of action, it was clear that there was a molecular recognition component involved in recognizing a conserved pyrophosphate group. I thought, that's exciting. My lab's interested in molecular recognition. It had an interesting structure. I thought, okay, there are some synthetic challenges here, like the amino acid, the non-proteinogenic amino acid alloindorecytidine. And then there was a macrocycle in the molecule where my lab works in macrocycles. So initially we got in sort of like, hey, let's, make some analogs and see how that works. And that was our initial entry into the area. But as we began working, we started making observations that were really unique to my laboratory's experiences and skill sets. I think what really clinched it for us was noticing that whenever we were making analogs that were active, they had a propensity to form gels. And whenever we made analogs that were inactive, they tended to be soluble. And it's like, oh, this correlation means something. And gels tend to mean a certain type of peptide aggregation. We thought of our Alzheimer's area where peptide aggregation is key in the production of amyloid peptides, beta amyloid aggregates, and other protein aggregates of alpha-synucleins. Like, I think this is an amyloid-forming peptide. We found it was, and we use tools that, again, are, my lab specializes in, like X-ray crystallography of peptides, to be able to find some really interesting and relevant structural aspects that gave us really valuable insights into how the molecule worked, how teixobactin gains its selectivity, and so forth. These days, I'm particularly excited because there'd been a problem that had been sort of in my mind for a while. This antibiotic has to be administered intravenously, but if it has a propensity to form gels and aggregate, that's a challenge. That's a problem for intravenous administration. And I'd been trying to think of a solution for a while, and then this came again from our work in the amyloid area, where there'd been a very nice paper that had impressed me, and a whole series of papers by Kizo in Japan, on how to make amyloid peptides more tractable, more soluble by an isopeptide linkage. And at that point, I sort of put that together and said, oh, okay, we could try that here, get the peptide in a soluble form that would then convert after it dispersed in the bloodstream. And that's looking very promising. My graduate student, Chelsea Jones, published a very nice paper in Chemical Science on this work. And now we're continuing these studies, and we would love to be able to actually, do further preclinical studies and eventually advance the compound to the clinic.
So there's a few questions I kind of have about that. One is perhaps that for people in the audiences that may not be as familiar with like peptides. Well, one is, what distinguishes a peptide from, like, let's say another drug? Like what, like, are they, let's say something like, I don't know, acetaminophen versus a peptide. Like, are there biological mechanisms that distinguish a peptide from, other drugs, or is there a chemical difference?
There are. And so many of the drugs that people use, like acetaminophen, are what are called small molecules. They're usually less than 1,000, often 500 molecular weight or less. They're often, but not always, given orally for some uses, injectable for other uses, but obviously pills are very convenient. And so this has been a mainstay of medicine. At the big end now, what's emerged as extremely important are biologics that generally are large molecules, often the size of antibodies, many tens, or let's say, 100,000 or more Daltons in molecular weight, a full-size protein, using biological mechanisms that our own immune system uses. So, for example, being able to target a receptor or something overexpressed on the surface of a cancer cell, and then to be able to perhaps deliver a toxic payload or deliver a radiological species to that cancer cell, so sort of targeted in that sense. Peptides are in that middle ground, generally bigger than small molecules, generally smaller than proteins, always made of amino acids, which is one of the defining feature of proteins, but generally lacking the folded three-dimensional shape of a protein. In general, what really characterizes a protein is having enough amino acids to fold into some well-defined shape that's related to how it works, to its function. Most peptides, not all, don't have that ability to fold, or at least not in the same way. Often the folding in proteins involves not only what's called secondary structure, but also tertiary structure. Secondary structure is local structure, like an alpha helix or a beta hairpin structure. tertiary structure is often packing together. And so you need a longer polypeptide chain to get that type of three-dimensional packing together. So there's no formal cutoff between a peptide and a protein, but often you could say, I don't know, 50 amino acids is usually perhaps at the lower limit for, upper limit for a common peptide, lower limit for a protein, but that's a very fuzzy number, and I wouldn't want to cast something hard in there. Anyway, most peptides then don't act in that same way that a protein does, creating this very large, well-defined three-dimensional shape, maybe even with cavities or pockets or many groups being displayed, but have more specialized functions. They may be ligands that bind into a receptor. In this case, they are something that binds to the surface of bacteria, working two or more at a time to get good binding, and then through a interesting mechanism breaking open the bacteria for teixobactin. Almost all, if not all, antibodies are going to be injectable. Many of them would be injected directly into the bloodstream or perhaps, under the skin. They're probably not going to, in general, go by way of oral bioavailability. So often for monoclonal antibodies, drugs, we're talking about things that are, for relatively severe diseases, because often, it's a clinical setting where the drug is delivered. Peptides often are not orally bioavailable, but not always. One of the leading examples of an orally bioavailable peptide is cyclosporin, that's not broken down in the GI tract and is taken up through the intestines. That's an immune suppressor. But most peptides are not going to be oral drugs. They're going to be often injectable, in some cases inhalable drugs that require a little bit more special need to have. The antibiotic teixobactin is what will be, if it makes it to the clinic, for the parent or for one of our what we call isobactin derivatives, will probably always be something that's an injectable antibiotic, given in the cases not of a simple strep throat, but in the case of an infection where you're going to be in the hospital anyway and you're going to die if that antibiotic resistant infection is not stopped, is not suppressed.
So I actually have a couple of questions. I guess actually kind of a three-part question then for you, because I'm not in the world of like peptide synthesis and peptides. But okay, so like let's say you have your target. So like you mentioned, you have your you kind of work in amyloids, but also the oh my God, I'm already forgetting teixobactin. Teixobactin. So you have two general frameworks to kind of work from. One is, so how do you like model, like do you just, how do you like decide which, let's say, amino acid residues are you predict will work the best? Like how do you kind of survey that landscape? Because you, like you mentioned, I mean, if you're putting together like 20 amino acids, like how do you know which ones are going to be the best?
So like when we started on teixobactin, we had no idea what its three-dimensional structure was or how it interacted. One of the first experiments we did was an alanine scan, where we basically just replaced each amino acid with alanine or D-amino acid with D-alanine and looked at what the key residues were. And then based on that, saw, alanine, is critical at this, the original residue is, the original amino acid is critical at this position. There were 4 amino acids that were like that, where the activity was just completely shut down if we replaced them with alanine. And it's like, okay, something very special is occurring with these. Later, as we began to get information not only from what's called structure-activity relationships, the alanine scan, but also from X-ray crystallography, and we began to get a greater understanding of how the antibiotic worked. We were able to formulate hypotheses. If we replace this hydrophobic amino acid with this larger and more hydrophobic amino acid, maybe we will get greater antibiotic activity. And to a good extent, that was borne out. So it was sort of, a little bit of trial and error exploration, then driving the creation of hypotheses, of ideas that could then be tested, and refining the understanding. Now I think we have a pretty good understanding of the antibiotic, particularly with the paper, the most recent paper that came out in Nature by the Weingarth group, which we had a small contribution to, that really brings together a lot of the understanding of the molecule into a bigger framework on how it acts upon bacteria.
So once you kind of do those studies, you know which amino acid residues are important, which ones you can kind of change and tune. Then I guess, so it's kind of a two-part question. One is, okay, there's a lot of stereocenters, I assume, between the amide bonds. So how do you control for that? And then two, you mentioned it before, you guys are experts in X-ray crystallography. I've never done X-ray crystallography. I've never had grow crystals, and that's just in small molecules. So is it easier to get X-ray crystals for peptides? Is it more difficult? And how useful is X-ray crystals for peptides? Because I know sometimes when we make crystals in the small molecule world, especially when you're growing crystals of catalyst, is it doesn't, the crystal structure of the catalyst or whatever does not necessarily mean anything as far as mechanism. So is that different for peptides, let's say?
That's a lot of interesting questions you've asked there. Let's start with the beginning one on stereocenters. So because peptides generally, not always, but generally are built amino acid by amino acid, and each amino acid has its own one or two stereocenters, generally one, but in the case of isoleucine and threonine, for proteinogenic amino acids, two stereocenters. You control the stereochemistry by choosing the correct stereochemistry of the amino acids. So that's not a particular issue. In terms of getting, was your next question on getting information it was whether X-ray crystallography is easier or harder for peptides. Having come from the small molecule school, initially my thought would have been harder. And these days, and this is much to the credit of my students, I would say people work very hard to make it look easy. We've adapted the tools of protein crystallography, which first of all involve aqueous solutions, allow minuscule amounts of material to be used, allow in screening of hundreds, if not more than hundreds, sometimes thousands of conditions with very short amount of, with smallish effort due to automation, robotic techniques, liquid handling robotic techniques. It can indeed be easier, but like in any sort of crystal growing, there's the question of persistence. So a lot of it is that 99% perspiration. The area that I'd say really is challenging is solving the structures of the peptide. So it's not just collecting the X-ray diffraction data of suitable quality, but it's then being able to determine the structure. And that often is challenging. And there are a number of tools that we've sort of adopted, particularly a scientist in my lab who earned his Ph.D. with me, Dr. Adam Kreutzer, has really been a master of this, solving the crystallographic phases using a whole slew of different techniques, really ingenious and passionate work on his part. So we published our initial efforts on doing this in a paper in 2015 titled A Newcomer's Guide to Crystallography, because I was asked at a conference, how do you guys do this? You make this look really easy. And then they said, hey, and can you publish a paper from the conference? And so I said, can I give the long answer to the question you asked to the editor of that journal, Joel Schneider, the editor of that special issue? And so we published this Newcomer's Guide as newcomers, and we've continued to sort of elaborate on this in, for example, methods in enzymology. So in some ways, it's easier in the sense that you can manipulate minuscule amounts of material in aqueous solution, unlike, say, most organic solvents like methylene chloride or diethyl ether. The rate of evaporation of water is way slower due to a higher boiling point and, very importantly, a higher heat of vaporization, which means minuscule droplets can be handled without evaporation and put into closed well crystal growing experiments. And so even a few milligrams of material is often enough to do hundreds, if not more than hundreds, of experiments and generate crystals suitable for X-ray crystallography. Often there's a second phase of optimization experiments that may take a couple more milligrams of material. But, in many cases, just a few milligrams is enough. In the case of small molecules, I think having only a few milligrams is really, really challenging just to have enough to manipulate to get crystals. So I think that was your second question. The question of what one learns, I think, is the really important thing. Because in general, with the peptides that we're studying, the covalent connectivity is not in question. Mm-hmm. It is the supramolecular assembly, how the molecules fit together, that really teaches us, and this is both in the amyloid antibiotic, in the amyloid aggregation area, amyloid oligomer area, and in the peptide antibiotic area. We've learned so much from crystal structures where it's been teaching us about folding and packing of the molecules. And that's usually the question. So often the peptides we study, when they pack, they do fold into well-defined three-dimensional structures where you do have multiple molecules coming together in fashions that may, in many cases, be teaching us about the biologically active species. So that's where really the sort of special insight comes from X-ray crystallography.
Now, in those crystals, let's just say in the amyloid area, it's probably, I assume it's well understood like where these peptides are binding. So when you're growing the crystal,
where they're binding biologically, oh no, that's a whole other can of worms. In fact, one that I haven't touched on, but we're using, among other areas, we're using fluorescence microscopy and putting fluorophores on our molecules, both in the teixobactin area, and in the antibiotic area, and in the amyloid area. But no, a lot of how do these peptides act, particularly in the amyloid area, and how do these amyloid oligomers, these small aggregates of peptides, act? This is a very open and interesting question.
Okay, because I was gonna ask, like, let's say when you're growing the crystals, the peptide crystals, in absence of not knowing the biological activity, then is that information still useful? Because like if it doesn't have the biological like aspect of it, then can you pull useful information still? I'm getting at, like, I don't like.
Yeah. Yes, I think the answer is you can get insights and get hypotheses about what's going on. So, for example, let me bounce to the fluorescent teixobactin examples, where we looked at my student Mike Morris, now Ph.D. Dr. Mike Morris, was interested. He wanted to visualize how teixobactin interacted with bacteria. And much like our sort of saying, hey, how do we make the molecule and learn something about it, and then discovering things further on, he also began to observe things as he looked at the interactions with bacteria, saw where it was binding to the greatest extent, how it was forming aggregates on the bacteria, which was something I don't think we appreciated at the time, being able to ask specific hypotheses about whether molecules are in intimate contact with each other, consistent with this supramolecular model that I've talked about. So as you do science in general, I would say that you start by asking simple questions. You design experiments, you perform experiments, you make observations. They, in turn, shape your framework of understanding. That, in turn, guides subsequent experiments. So what might start as kind of a simplistic or naive question often can, in the hands of a good graduate student or a good researcher, lead to really profound insights.
Yeah, I think peptides is certainly a really fascinating subject, and I love picking people as the experts about this kind of thing, because I'm not into it, but I love kind of seeing how especially alpha helices and beta sheets, beta hairpins, how it's like you mentioned, it's the non-covalent interactions that are really kind of driving a lot of these biologics, right? The non-covalent things like the pi stacking, the hydrogen bonding and donor interactions that are driving a lot of these things, which I think is really cool. And it's not the physical bonds between the elements, basically, that comprise them.
Absolutely.
That's really cool.
You come back, so I want to bounce back to one thing that I was talking about before. You asked about how one learns. I think you were asking about this, or how you decide what, I think you put it, amino acids to change. So in the case of teixobactin, bacteria have, through many millions of years of evolution, they don't make antibiotics for our benefit. They make it for their own evolutionary benefit. And through millions of years of evolution, the bacterium that makes this Escherichia terrae optimized this molecule to essentially carve out its own eco niche and poison other bacteria to have access to resources. So this is driven by evolutionary biology. So one of the questions that we've been asking is, can we, not having cajillions of bacteria over millions of years to create different or better antibiotics, can we use what we've learned to design new antibiotics either from scratch or partially from scratch? And thus far, we're finding it really challenging. We've made some headway, but I would say that right now we come back to this issue of nature still being able to beat out design, and we want to learn how to beat out nature, or at least compete with nature. This brings us full circle to the steroid hydroxylation problem I mentioned earlier, that served sort of as a lodestar, as a guidepost for the Breslow group and Professor Ron Breslow, where here's a problem that was so tough and so big. And eventually, I think they were able to sort of partially crack that problem for real over the course of decades. But here's a problem that's so big, which is basically, how does an enzyme take a steroid and functionalize at one particular site and one particular stereochemistry to create a hydroxylated steroid. And this still remains a tremendous challenge. It is there in catalysis. How do we go ahead and generate a metal-based catalyst that can activate a CH bond, which I presume gets close to the language that you and your group and the group meetings that you partake of, or the seminars.
Yeah, it's certainly more within my area,
focus on. It ties into areas where one's doing engineering of enzymes, meaning you go ahead and you find an enzyme that does something, and then you come up with ways to use it, improve upon it. You know, one of the groups that we've benefited from is Hans Renata's group, who's gone ahead and come up with some really nice chemoenzymatic synthetic tools for CH bond activation. That's another way. And then, yet another way becomes, how do we design stuff from, complete scratch where we could just sit down with a piece of paper or ChemDraw, dream up a molecule, make one particular chemical compound, hit a home run, and we're still a long way from that. So lots and lots of challenges out there for the future.
Yeah, I think ultimately, the closer we get to how nature and the enzymes of their behavior, there's always an area of research to try and do those things. And it's exciting to see where that takes us. I kind of want to circle back a little bit because, how does one get into like enzymes and the things that you work on with peptides and stuff like that? You had gotten your you got your bachelor's degree from Columbia. You worked with professors Jacqueline Barton, Thomas Katz, and David Tyler, respectively. Then you kind of did your Ph.D. at MIT as well as a postdoc. But I want to start really kind of at the early beginning. How did your initial interest? Did you even have initial interest in chemistry at a young age? And where did all those things start?
I was really fortunate. My dad was a professor, and so I had access to a lot of science stuff. I got hooked on chemistry at probably about age 8 by electroplating a penny with nickel, and it's so cool to be able to have a copper penny go in with some electrodes connected to it into a solution of electrolyte with a suitable nickel electrode, and to be able to pull out a nickel coated penny, and just seeing that transformation. And that's sort of the essence of chemistry, the science of matter and its transformation. And I was hooked and wanted every sort of theme and variation on that, copper plating and silver plating and zinc plating and anything that I could think of, in electrochemistry and so forth, all in my basement, where I was basically able to eventually have quite a home laboratory, including a fume hood that I built.
You built a fume hood?
Yeah,
with the proper ventilation.
Yeah, I used a vacuum cleaner motor for the ventilation. I made the cabinet out of aluminum. It was painted on the inside to resist corrosion. It had a plexiglass sash on it, and I even put in a cup sink for running water.
That's sick. That's freaking sick. So how did you, your initial interest, I assume, through middle school and high school, you're always interested, like you mentioned, your father was a professor. What what kind of drew you to go to Columbia and start with undergraduate research?
So I actually, again, was really very fortunate, privileged, if you will, was I was able to get into a laboratory as a high schooler, not in the chemistry department, but in my dad's engineering school in a different department called the Department of Mineral Engineering. And so I was doing synthetic organic chemistry back as a 10th or 11th grader, and I just loved it. and had a lot of freedom there. And so when I went into college, I definitely wanted to get involved in research. My first lab, as you mentioned, was Dave Tyler, who was my freshman chemistry teacher and basically like professor, and was like, hey, would you let me into your lab to do any sort of, I'll wash glass or I'll do anything you want. And he nicely gave me a research project. But my love of organic chemistry, I went back to that, which was my sophomore professor, Tom Katz. Actually, I may have gone to him before I had a class with him, and he kindly let me into his lab. And along the way, I did a little stint for a PChem class with Jackie Barton that resulted in a paper in ChemCom.
Oh, really cool. So, what were you working on as an undergraduate student? 'Cause I know it's got to be one of the most valuable resources. As early you can get into undergraduate research, I don't think it just prepares you so well moving forward. The earlier you can get started and the earlier you can kind of learn the little tips and tricks, the earlier, the better off you're going to be in the future. So I think initially my Dave Tyler basically put me on a computer-based project that I wasn't super excited about. It was, computational molecular orbital calculations, and just didn't resonate with me. And I think I asked for something experimental and got to do some really, really cool photochemistry with some tungsten complexes, and that was fun. But I already knew I loved organic chemistry and slopping around with organic chemistry. So it was sort of a natural to transition over to Tom Katz's lab. I was working on the synthesis of helical aromatic compounds called helicenes, and maybe not by accident, to the scientist I am today, that one of the epiphanies in this work was an X-ray crystallographic structure that identified a surprise molecule that I got that then served to guide a synthetic route that I then worked on. So basically that power of seeing what you've made and understanding what you've made was so powerful to me. And continued in my graduate studies as a small component and in my early studies as a professor. And then as we got to bigger and bigger molecules, away from small molecules toward bigger peptides, disappeared and then reappeared after a fortuitous connection with Professor David Eisenberg at UCLA, who basically reintroduced my group. Actually, that's only partially true. I had a fantastic graduate student who introduced his undergraduate, Aaron. So the graduate student was Omid Kakshar. He introduced his undergraduate student, Aaron Lin, to growing crystals. And then we learned with our peptides that the protein crystallographers couldn't help us, and the small molecules crystallographers couldn't help us. And it really was David Eisenberg's group that helped us and sort of got us started in this mesoscale, this mid-sized peptide crystallography that was sort of separate in some ways from protein crystallography and separate from small molecule crystallography. Yeah. So anyway, but I loved building molecules, and that was where I went in my graduate studies. And I loved how molecules fit together, supramolecular chemistry, which is where I went in my postdoctoral studies. I had no experience with peptides, didn't even know they were interesting as a grad student or postdoc, but figured since it would be of interest to people, and since I wanted to explore various ideas, that bringing in biologically relevant ideas with peptides would be appropriate, and then that sort of took off. Yeah, I was gonna mention that, I guess the first thing I'll ask is, was the transition from an undergraduate, was graduate school always on your mind? And I always ask professors this, at what point did you being a professor, really something you really wanted to do? How did you, when did you kind of know that? or was it kind of something that just kind of came about naturally?
Again, as a faculty brat, I knew it was a nice life. I loved universities. I'd been to Columbia visiting Columbia since I was visiting my dad there as a kid. Visiting his laboratory. I knew laboratories. I knew laboratories are fun places where a lot of exciting things happen. So it always seemed to make sense to me that was what I wanted to do. And then, this is a two-edged sword. There are, in terms of access and privilege, it means that people who, come from academic families, and particularly, science academic families, have more access and also have more of a roadmap to go on. So there's a ton of people who's, in academia, whose children are also pursuing PhDs, in some cases to go on in academia. And yet other people who might never know this is an exciting career option. So, yeah.
Now, during your graduate studies, your advisor was Professor Rick Danheiser at MIT. Now, you were doing, we mentioned, you were kind of doing organic chemistry, and you're doing functionalization of acetylsilanes and making beta lactones and alkenes. And then for your postdoc, though, that was also at MIT, but Professor Julius Rebek Jr. But that was in molecular recognition. So kind of there obviously was a difference. And so what was it kind of a natural transition? Was there a certain experiments that you would been conducting that kind of piqued your interest, or was there one experiment where this is really interesting, I want to pursue that aspect of molecular recognition as opposed to doing organic chemistry?
Well, as I said, I loved making molecules. I loved running organic reactions and having product. You have an idea in the morning, you plan out, or maybe the night before, you plan some experiments, you mix some chemicals to test your idea about a particular reaction. You characterize the products of the reaction. Maybe you isolate a pure product and characterize its yield. It's a very fun sort of cycle, and it fit well. I mean, it's addictive, fit well with synthetic methodology, which was the area I did my Ph.D. in. But, if you look at the sort of things I would always, doodle and think about, it would be, I wonder if we can make this molecule or the shape of this. It would be making stuff that does stuff in the simplest level, making organic molecules that do something, which really was a natural fit. So, in other words, not just letting nature be the architect of the molecules, but being able to be the architect as well as the builder. And that was a fun idea. And that fit very naturally to molecular recognition and supramolecular chemistry, where you're not limited by what's found in nature, and you're often able to say, I wonder if we could make a molecule to bind this particular nucleobase or this particular substrate, or nature can do this. How could we do this? Well, without using, how can we compete with or improve upon nature, which is one of the themes that I've been dropping for a while. So that fit very well. And when I started my faculty position, I had some ideas involving molecular recognition, some ideas involving three-dimensional shapes of molecules. And in these ideas, I incorporated, nucleobases and incorporated peptides into them, and basically continued to explore these ideas. And these are themes that have fascinated me and have perked up again and again. I think that some people, and again, I'll come back to one of the inspirations for Ron Breslow on how do enzymes work. It's such a profound question that sometimes these influences, how do molecules recognize each other in water? How do you get hydrogen bonds in an environment where you have 110 molar, 55 times 2 hydrogen bond donors, H2O, water. And so asking these types of questions sort of become these themes that, how does one do that? That kind of percolate threads that drive one that then get asked in different contexts and with different relevances.
Something that I like to always ask professors too is, especially early on as a graduate student, like you might be facing a lot of like unsuccessful reactions and things aren't working. Maybe even as a postdoc and even as a new professor, you're also going to be experiencing like some hardships as far as like unsuccessful reactions and stuff like that. Now, do you recall any like experiments or moments where it all kind of clicked and like it all started working? And on top of that, what's like your advice for, let's say a lot of like unsuccessful reactions? Because something I like to say to myself too is like, just because your reactions don't work doesn't make you a bad person. One, right. So, and because science is always about cutting edge and doing new things are going to take time.
So you're asking a bunch of great questions. So power of observation is important. And, I always, particularly in terms of running reactions, tell my graduate spectroscopy class that NMR and IR, mass spec are your eyes. And the goal in running a reaction is not simply to get the desired product. It's to learn what's going on and then figure out what are the pathways that are interesting and relevant. What are the pathways you want to shut down? What other reactions are occurring? Not simply sort of blindly throwing darts and saying, well, today I think I'll run the reaction at 60 degrees and see if that gives me a better yield. Today I'll run it in acetonitrile. There's a place for that, and the area called design of experiments has become very important. But there's also this looking and saying, okay, the reaction, I keep recovering starting material. Is that occurring because my reactant is getting quenched? Is it occurring because the reaction isn't running long enough? Is it occurring because the reaction's in equilibrium? And trying to tease that out and then say, okay, well, if it's this way, if it's in equilibrium, how do we drive it? Maybe the answer is Le Chatelier's principle. I have examples where it's, drive the reaction in a solvent where your desired product precipitates out. And then other examples where you look and you say, oh, wow, okay, my reactant is decomposing, but I notice that it decomposes when I take an NMR spectrum in DMSO, it decomposes far faster than when I take an NMR spectrum in chloroform, and then recognizing maybe through an IR spectrum that reactant is hydrogen bonding to that CH in chloroform, and then saying, we can use this principle to make the reactant more stable so that it can react longer. So it's really this power of observation, being open to serendipity. You mentioned beta-lactones. That was a serendipitous discovery that IR spectroscopy, my eyes there, told me about, and said, hey, you were trying to do X, but Y is occurring, and Y, and then sort of that power of thinking and saying, and Y is even more interesting than the X that you were trying to do. So there's a lot of this. So sometimes it's push harder, as I said, through tools of observation and spectroscopy. Sometimes it's take a step back and say, okay, we can do this in this other way and work around. I know that if people are always taking steps back, and I've seen people do this, then, that doesn't work. So that's, the workaround to the workaround to the workaround. At some point, the project just becomes so ugly that nobody cares anymore, or it's not worth it. So it's that balance of tenacity and, an observation with sometimes the resilience to be able to say, okay, we need another approach. And sometimes the answer becomes, I've thrown everything I can at this. I'm not going to crack this problem. And it's knowing when to say that, or at least when to say, hey, I need something else to keep myself motivated. I'm still going to work on this, but I need this additional project to keep myself motivated and excited. And it's a balance.
Yeah, that's some really, really good advice and very insightful. Some interesting questions I'd like to ask you too is, because you went to Columbia, MIT, the East Coast life, Northeast, and now you're at UC Irvine. Where do you stand on, East Coast, West Coast life and outside of chemistry? Like, what were some of your activities? So, like, what were some of your activities that you did, outside of, being a graduate student, undergraduate student? And then what are some of the things you like to do now, like, being outside of professorship out there in Cali?
Obviously the weather is better. I guess in the East Coast right now, they're getting a nor'easter, or maybe they just had a big storm, power outages, airlines out. I don't miss the winter. I chose UCI because it was the best department. It's a great department. It's superb department. Collegial, it's values mentorship of the graduate students. People support each other. There's great science going on. There's great facilities. So it's been a really wonderful place in that regard. Outside of the lab, that's an interesting question. I mean, I love what I like my time at home. I like getting out to restaurants and the local theater here. It's been a while since I've gotten out to the movies. Don't know if I'm getting back to them.
I think I haven't been in the movie theater since like before 2020, and I don't know if that's a consequence of like just not movies I'm interested in, or like I don't know what that. I don't know. I do kind of miss the movie going experience, but I don't. But there hasn't been like a real movie where it's like, wow, I really want to get out there and go see it.
Travel is something I enjoy, and it's very congruent with my professional career. Times, you can go ahead and travel to interesting places for conferences, and then spend some time, or get an invitation to speak somewhere, and then spend some time. That's a lot of fun. Boston and New York are great cities. Irvine is more of a, it's big. It's 300,000 people, or close to 300,000 people, but it's not as, urban.
Right.
And it's suburban, California suburban. I like Boston. It's a happening town. I like New York, although I think these days it's just maybe a little too much. In terms of the city, it's I think it was a great place to be a student for college, but Boston's a great city. So I think that sort of covers the things I like to do. I like to cook. I like to get together with friends.
Any particular cuisines, or cook anything?
Toward the European influence, French, Italian influenced, contemporary American too. But it's, in part, let's face it, I liked mixing chemicals. These days I have, almost no chance to get into the laboratory other than to, be with my group members and talk with them about their own experiments, or look over their shoulders. So, to some extent, this is the experimentalist in me, and I generally don't cook from recipes.
Yeah, well, you gotta experimentally try it. If it's if you're not just throwing things together, you know, are you really a chemist? I guess the last thing I want to pick your brain about is like, do you think has been like the most rewarding experience, like now as a distinguished professor, and running your research group? Like, what has been like some of your favorite moments as a professor at UC Irvine?
I mean, I'm super proud of my group and watching their own accomplishments. I think, honestly, seeing the science through their eyes, seeing their careers progress, seeing people graduate and get, start on their own, in their own jobs. I'm super proud of that, and, really, really pleased to be a part of it. The other thing that, that you didn't directly touch on when you said Columbia, MIT, and UC Irvine is that we're a public university. And, when I started, I really didn't appreciate just what a great thing the University of California system is. We've got 10 excellent campuses here. A couple of them are, maybe less well developed. One of them is very, very new and is still starting. But UCI was relatively new. It was barely 25 years old when I started, and it's grown tremendously. We've gone from just opening our second building that houses chemistry when I started to now having 5 buildings that house chemistry. One of the things I really didn't appreciate is just what a valuable service public university is, and how special, California in particular, where, many states you'll have 1 or 2 strong leading public universities. We've got a whole huge collection, the UC system, 10 campuses. The Cal States, which are less research focused, they grant MS degrees as well as bachelor's degrees, but generally not Ph.D. degrees, and community colleges. And this has been a real engine of success for California, and also an engine of opportunity for our students. Roughly half of our students are first generation, undergraduates are first generation to go to college. That's huge. That's, incredible. People whose parents may be working in a nail salon or, a hair salon, or, doing other sorts of difficult work or agricultural work, whose kids can afford to go to university and then go on to professional careers. So that's huge. And many of our students work incredibly hard. They're working jobs to support themselves and so forth. I really have grown to appreciate this. Coming from, Columbia and MIT, I don't think I saw the value, saw just what fantastic value a public university brings. We're not cheap to go to, but by comparison, again, I'm thinking mostly undergraduates, by comparison to going to USC or Stanford, there's a lot more value there. Those are great programs, but it's also the difference between, many tens of thousands of dollars more in tuition for also an excellent, education. So again, I do look at this as being really, really important as a mission.
Well, Professor Nowick, I'd like to thank you so much for your time and consideration coming on to the show today. I'm excited to see, your future work in those peptides, those teixobactins, and the amyloid derivatives. It's an exciting time. Are you doing any lectures coming up, or are you going to any conferences soon?
I'm going to be off on sabbatical in France at an institute in.
So we'll have to fly to France to come talk to you. We'll have to fly to France to come talk to you.
So I will be off there, and I'll be giving some lectures in France while I'm.
We're going to France, Paris, or
it's Montpellier.
Montpellier. So gotta catch a football match out there.
Someone else I think mentioned that they have some leading sports teams there.
Mm-hmm. Well, I wish you the best on your sabbatical and your group's, future research. I think it's really cool stuff. I think that's all, folks. I'll see you next time on the next episode.
Thank you very much.